Hello everybody. Today the video topic is microfluidics and fundamental fluid flow equations, constructing them with the Reynolds Transport Theorem. With the help of Reynolds Transport Theorem, we will be constructing these equations. First of all, let me start with outlines of presentation. So we will be discussing about microfluidics, its advantages and limitations. First of all, what is microfluidics? We will be going through its advantages and limitations, modeling fluid mechanics problems, with different approaches such as Lagrangian approach or Eulerian approach. We will then move on to the physics of microfluidics, where we will be discussing about main fundamental equations to model any type of microfluidics problems. We will see flow as a function of Reynolds number and non-dimensionalization, flow models in two-phase flow situations, further applications of Reynolds Transport Theorem in deriving conservation of mass, momentum and energy equations. We will then deal with scaling analysis and dynamic similarity, and I have a video on NPTEL on video on finite element simulations of liquid-liquid two-phase flow. We have some backup slides. Starting with this, the physics of microfluidics is a branch of fluid mechanics in which we will consider fluids that are confined in structures of micrometer scale, that is, structures that have at least one dimension lower than a millimeter. At micro scales, the dominant forces are different from those we experience at the macro scale, and flow typically exhibits properties that can be exploited in microfluidic devices. So in micro scale here we can see a coin size, about a coin size, the entire reactor has been impregnated into it. We are having this reaction loop, we are having a circulation pump, we are having metering pump, right concentration loop. This is a microfluidic reactor. So figure 2 is a microfluidic reactor and figure 1 is a microfluidic chemostat device of our coin size, where 2 figure we can see that synthesis of 2-deoxyfluorodiglucose has been conducted out. So where the definition is that one dimension, that is the structures that have at least one dimension lower than a millimeter, can say them as a microfluidic device. So the emergence of microfluidic in the recent decades has provided an unprecedented precision in continuous flow technology, bringing new capabilities to wide range of fields. So from biological analysis and chemical synthesis to optics and information technology. In microfluidics, we are having surface forces more important than inertia forces. So as surface to volume ratio increases, we are getting, for the same reactant inlet, we are getting more product output. But to scale up those things, we can also arrange them in a parallel, but that will come later on. So why should we study microfluidics, or why is it so important? So we are having small reagent volume microreactor and footprint, as one may expect when we are working with a significantly smaller volume of materials as one does with microfluidics when compared to bulk batch chemical reactions. Substantial cost savings can be made, and can be easily scaled up. Second one is the important point is that the selectivity of microreactors, as is often the case with chemical and biological reactions, multiple products can be generated from a given set of reagents dependent on local conditions of the reaction. With the control over these conditions granted by microfluidics such as temperature and residence time, individual compound among multiple that could be produced by a given reaction can thus be selectively produced with a high degree of precision. So what does this mean is that we can control the selectivity of our product output to a greater degree of extent compared to macro reactors in microfluidics. So then again, the third most important advantage is that rapid safe reactions can be carried out in microreactors. What does that mean? First we discuss that. In regard to relative reaction times of microfluidic reactors and bulk reactors, there are few fundamental things limiting the ability to make a direct comparison in all respects. Bulk reactions are often performed with more time than would be necessary to reach the equilibrium point of reaction. In order to ensure that the desired reaction has reached to completion, chemical reactions in microfluidic devices can be performed with more inherent safety than before, and with the ability to handle high pressures and temperatures at small scale. By virtue of the fact that only small volume of reagents are used in microreactors, reactions that are particularly reactive, explosive or toxic can be mitigated with relative ease. So what does this statement mean? Basically, the statement signifies is that there are highly exothermic reactions such as nitration of toluene and um, such as mixing of certain reagent explosive chemical reactions are there, such as manufacture of sulfuric acid, or the mixing of caustic soda with any um, uh, highly chemically active reagents. So these reactions actually are highly exothermic, and there is a tendency, or there is a risk that explosion might occur. So if we deal with those exothermic reactions in a small volume, so we can actually increase our safety to a greater extent while keeping our product output without comparison with the help of product output. So how we can increase our product output like that those of micro scale? We can actually scale up the microfluidic reactors. That is, arrange them in a parallel way. That is another kind of achieving, or we can say subsiding the negative side of microfluidics with the help of scale up technology. So that we will be discussing in the next slides. Now, scale out potential. What I was meaning to say with this is that the scale up potential of microreactors, in contrast to scaling up of microreactors, that is increasing. If we increase the characteristic dimension for increased production, the true strength of microfluidics comes in scaling out. Now, what does the scaling out mean? These systems see, if we see that instead of increasing the size of microreactors, scaling out simply denotes the increasing the number of microreactors in order to produce a parallel network. So reactors are increased in order to produce a parallel network. The advantages comes from the fact that by using multiple reactions of the same size, the chemistry performed in each one remains same. So we are not changing the chemistry, and the product output is remains same, but the combined product output from all those parallel branches actually leads to an increase in our product output. So one remains the same state at any level of scaling out. So some limitations, or we can say some discussing points are there for microfluidics. Up till now, we see microfluidics as enabling or replacing technology. We see it as an enabling technology. So why so? Coming to that point, while it is undoubted that microfluidics technology can enable a wide range of chemical process, it is viewed as an enabling technology rather than replacing technology. Because the use of microreactors can bypass certain limitations that exist in conventional process. Of course, these are true process condition while carrying out hazardous reaction. On the other hand, for reactions that are not problematic or hazardous, such as those not highly exothermic, or for those dominated by slow reaction rates, rather they are being limited by rate of heat or mass transfer, the advantages of granted by the microfluidics becomes less apparent, or in fact non-existent in those cases. Similarly, those reactions that take advantage of bulk forces like gravity, buoyancy, such as distillation, centrifugation, and phase separation may be better suited to large-scale operations than integration with microfluidics. So other practical issues are that the production volume capability. When only a small volume amount of reagent are involved, only a small amount of product will be consequently be produced. While this can be effectively sidestepped to some degree through scaling out of microfluidic systems. So modeling of fluid mechanics problem. This is a critical topic and of great importance. How do we model a fluid mechanics problem? There is a Lagrangian approach. Two most popular methods are there. One is Lagrangian approach, and another one is Eulerian approach. Coming to Lagrangian approach, we follow a fixed packet of mass system where system can change size and shape, but we always follow that fixed packet of mass. We treat the mentioned particle as is in motion. Coming to Eulerian approach, so it deals with fixed region of interest control volume. So where it can change size and shape, mass can cross the boundary. So if we take the example of a centrifugal pump, water is coming in and it's moving out. Pump is doing its work. So what does that? If we focus on pump, we can say it is a control volume where mass is entering and leaving, crossing the boundary, and the control volume can change size and shape. But in Lagrangian approach, we are following a fixed packet of mass. So we are concentrating on that lump of fluid which is coming in and coming out. So in this case, mass cannot cross the boundary. So this is the main difference between the Lagrangian and Eulerian approach. So we treat in Lagrangian approach the mentioned particle as in motion, but we always follow that fixed packet of mass. So many of the laws in our continuum mechanics or in mechanics are basically in mechanics are basically such as Newton's second law. So these are on Lagrangian system, not an Eulerian system. So these are valid for a system, particular system where we are following a fixed packet of mass and not a control volume approach. So next, coming to the next slide is the physics of microfluidics. So how do we approach, how do we get a know how the physics of microfluidics, how the fluid is behaving or microfluidics is happening. So main fundamental equation is Navier-Stokes equation, which is derived from conservation of momentum, in special case of conservation of momentum equation. So where our density and viscosity remains constant. So it's actually in this Navier-Stokes equation we find that we are having a del U by del T part, and we are having a convective velocity part, that is divergence U, and we are having a pressure forces part. Right side we are having a forces, this is one due to diffusive velocity due to diffusion, and we are having an external forces part. So in microfluidics what happens is that our convective flow or convective forces become least important in comparison to the diffusive forces, the molecular transport forces. So we basically focus on this molecular transport forces in microfluidics, and where our inertia forces are least important and surface forces are more important here. As we can see, it's a non-dimensionalized Navier-Stokes equation. Why we need non-dimensionalization, we will come to it in our subsequent slides. So first of all, just to give you a glimpse, is that the key variable u, that is velocity, depends on several parameters such as geometry, viscosity, density. Here u is dependent upon microfluidic channel geometry, viscosity or density. Not only macrofluidic channels also geometry, viscosity, density. So if we conduct experiments to see how the u varies with all these parameters, we have to design hundreds if not thousands of experiments to do the same. Cutting down the number of experiments actually and for extracting the technique for extracting the key controlling parameter is done by non-dimensionalization. So what does non-dimensionalized do? Always as the name suggests, is non-dimensionalized. The terms present here do not have any dimensions. So in this way what we achieve is that we find out the key controlling parameters, in our case here Reynolds number, and we see how the Reynolds number varies with this parameter. So in this way we cut down the number of experiments to determine how the flow behaves in microfluidics as well as macrofluidics channel with Reynolds number. So here u, just to give you the definition what these terms mean, here u is fluid velocity, rho is our density of the fluid, v is the pressure field, we are having a kinematic viscosity, f is nu is our kinematic viscosity, and f is our external acceleration field. So now flow regime as a function of Reynolds number. We are having a non-dimensionalized Reynolds number in equation 3. So in laminar flow in microfluidics channel, actually in laminar flow, not in microfluidic channel, in laminar flow what does happen is that our convective forces becomes less important. We are having dominant diffusive forces, viscous forces. To be precise, viscous forces are more dominant compared to convective forces of convection. So here to be precise, advection. So here our right hand side of equation number 3 becomes more important. In this way we are having a laminar flow, equation 3 dominates. For turbulent flow, if we come to equation 3, we see for turbulent flow our advective forces, or actually we can convective forces. Convection is advection plus diffusion. So advective forces role is much more, or we can neglect if we take the ratio of the two terms. We can say the stronger part is lies with the advective forces. So here advection becomes more important in comparison to our diffusive forces in turbulent flow. But in turbulent flow, of course, we do not have just like turbulent flow. There are 3 separate layers. Actually, we are having layer, we see a turbulent flow flowing over a flat plate. So we are having a viscous sublayer. We are having a buffer zone which is represented by zone 2 there, and we are having zone 3 which is turbulent flow, where the flow is fully turbulent. So zone which is close to the wall or close to the plate is somehow laminar sublayer exists. Some kind of laminar layer exists, since there is some adhesive forces between the channel material or the flat plate and the flow. So flow is not fully developed in this layer. Now to determine the how much thickness of boundary layer exists. The boundary layer is where our velocity, the flow velocity, reaches 99% of the free stream velocity. To determine that thickness of the boundary layer, von Karman gave equations. So that is not the subject of this slide, discussion of this slide. We can discuss von Karman in another slide. After that, we move to the next topic: separated flow in model in two-phase flow. As we can see, two-phase flow or multi-phase flow are very important in context of microfluidics. We often see multi-phase flow in varied situations in the form of gas liquid two-phase flow, liquid liquid two-phase flow, solid liquid two-phase flow if there is slurry. So these are common occurrences of these two-phase flows. So in this context, we can say we are having separated flow model and we are having homogeneous flow model. These are two more popularly used models. So how do this model design? We will just discuss about the basic fundamentals here. So separated flow model is a one-dimensional separated flow model in which the phases are considered separately. So in this model, actually the separated flow model takes account of the fact that the two phases have different properties and different velocities. So while it's having that the two phases are having the phase 1 and phase 2 immiscible phases, those both of the phases have different velocities with respect to each other. There is a slip between those phases, or there is a drift velocity between them, to be precise. Now the equation of continuity. In the equation of continuity, we are having two other phases with each other. So we are having, if we write equation of continuity or mass balance equation for the two phases separately, we are having a rho 1. Rho 1 is denotes the density of the phase 1, and rho 2 denotes the density of the phase 2. We are having alpha. Alpha, what is alpha? Alpha is the volume fraction of phase 2. How much phase 2 is there in a two-phase multi-phase mixture. If phase 2 is completely present, then alpha is equal to 1. If phase 2 is completely absent, then alpha is equal to 0. So this is the definition of alpha. If we go by the density of mixture, we can get the idea or hold on such as alpha rho 2 plus 1 minus alpha rho 1. In this way, if we come the equation of momentum equation, first of all, in equation of continuity, we are having terms the S1 and S2. These are the external sources of matter, and we are having a divergence of this velocity vector. So, coming to equation of momentum, we are having this part rho 1 del v1 by del t plus v1 grad of v1. This is actually rho 1 dv by dt. dv by dt is a substantial velocity derivative, substantial time derivative of velocity. So in this way, in the substantial time derivative basically analyzes, what does it analyze? The LHS analyzes the flow in a stream, in a river, the change in the concentration or change in the mass or momentum with respect to a free stream velocity, as if you are flowing with a free stream of in a canoe and measuring the velocity change with respect to your canoe and free stream. So that is given by substantial time derivative. So this is basically a Lagrangian term, LHS. Then we are having a body forces, we are having a viscous forces, and we are having pressure forces, which is given by grad of P. Now in the similar manner, we can derive the energy equations for phases separately. Now, and second one most popularly used models are homogeneous flow models in two-phase flow. What does this theory derive? The theory provides the simplest technique for analyzing two-phase flow. Suitable averaging properties are determined, and the mixture is treated as a pseudo fluid that obeys the usual equations of single component flow. So we average suitable average properties we determine, and we treat the mixture as a pseudo fluid that obeys the usual equations of single component flow. Here the pseudo properties are one density, second viscosity, etc. are weighted averages and are not necessarily the same as the property of either of the phases. So in this manner, what we do in homogeneous flow model is that we do not separately write equations for each phases in a different manner, but we just assume them as a pseudo fluid. We average the properties of the fluid such as average density, average viscosity, and then we write equations as if there was a single fluid. So these are the equations of continuity, momentum, and energy equations. McAdams derived this correlation in 1942 for determining two-phase flow viscosity, del of x by mu g 1 minus x by mu f. X is the quality of the flow, how much mass fraction of the mass flow rate of phase 2 in comparison to total mass flow rate is given by x. This is the McAdams definition. Alpha deals with the volumetric flow rate of phase 2 with the total volumetric flow rate. In the similar manner, how these equations of continuity, momentum, and energy equation we can derive with the help of Reynolds Transport Theorem, we are coming in subsequent slides. That will be discussed. Now we come to the Reynolds Transport Theorem. So in Reynolds Transport Theorem basically relates our Lagrangian part, the LHS dV system by dt. This is a substantial time derivative with the Eulerian part. This is our Eulerian part, this control volume, and this is the net efflux velocity or any property which is coming in and exiting out of the system. So in conservation of mass, how we derive conservation of mass? V is if any property, intensive property which is independent of mass, which we are measuring. It may be momentum, V may be momentum, V may be energy, V may be mass, or the property which we are interested in, V. V can also be electric field if we are talking about, or something like that. So if we zero in this Reynolds Transport Theorem, we find that LHS must be equal to 0 due to conservation of mass. So as we can see, rate of mass in minus rate of mass out plus rate of mass generation minus consumption equal to accumulation is a standard definition which you can find in Himmelblau or any good book on chemical engineering process calculations, how to conserve this principle. Actually design equations. These are actually design equations for chemical reactors and in every aspect in microfluid mechanics and all. So when there is a conservation of mass, or conservation is happening, and there is no generation and no consumption, and if the system is at steady state, there is no accumulation. The LHS dV system by dt, there is no accumulation of the property. We can write it as 0. So by this definition, it goes 0. LHS becomes 0. Now we are left with our RHS, which is our Eulerian term, and this extra term for net efflux of property, net efflux of property in and in the total of the in and out of the property in the system of our interest. So here what we can see is that there is a control surface. We need to convert it into control volume. So Maxwell's famous formula, actually famous theorem which is more popularly known as divergence integral theorem. So divergence integral theorem, if we see a control volume which is composed of many small sources which act as a source or sink. So divergence of F be any property, may be force, it can be force or electric field or something, mass, momentum, energy. So combination of all those sources or sinks of mass in that control volume is equal to, in his theorem he proved that they are equal to, as if in a bound control surface with F vector dot dm, that property force or any property which is unit normal to the surface area vector of that small infinitesimal property of interest which we are interested in. With the help of this theorem, divergence integral theorem, we convert our rho b, v r vector dot eta cap, v r is the relative velocity with respect to this fluid flow in the direction of our unit normal vector, that is in the direction of a small infinitesimal small vector. We are not interested in perpendicular or in some angle, but in a direction normal to our area vector. So that is given by rho v vector dot eta cap is converted into divergence of rho v dv with the help of divergence integral theorem. Now we do some simple integration, and we arrive at our equation of continuity equation. So we can see how we can easily actually use this Reynolds Transport Theorem as a tool to solve the conservation of mass, to reach conservation of mass, momentum or energy equations with ease for any arbitrary, any problem of our interest. Now we move to our conservation of momentum, application of Reynolds Transport Theorem for deriving conservation of moment equation. So we write our general Reynolds Transport Theorem where 1, 2, 3. 1 represents change within system, which is the Lagrangian term. 2 is our Eulerian term, which represents change within control volume. We are having 3 stuff that crosses the boundary. Stuff that might be electric field, there might be force vector, might be velocity, might be mass, might be momentum, might be any energy, anything which that crosses the boundary, our control volume, that control surface. So which is enclosing the control volume. So here for our conservation of momentum equation, we create all the forces which are necessary, that is summation of sigma f. So our number one term in the equation 1 term, or LHS, becomes sigma f, that is summation of all forces associated with our system of interest. Then LHS is given as del del t of E rho b dv plus area vector integration of the closed area A rho b u vector dot eta cap dA. So if we consider LHS, we are having B property, that B is total forces acting on the control volume. What are total forces acting which are acting on a control volume? It is composed of body forces acting on the volume and traction forces acting on the surface. Traction forces act on the surface. So traction forces are composed of pressure forces, shear forces. The traction forces which are normal to the area vector of the surface are known as pressure forces. Please note that. The traction forces which are not normal but at some angle inclined to the surface with the area vector of the surface, they are shear forces. Now traction is composed of traction force vector and body forces vector. So we can write our LHS as volume integral of rho fb dv and shear t dot eta cap dA. Now you see here that I have given 2 lines under below tau, that is shear stress. Why? Because tau is a second order scalar, second order tensor. So first zero order tensor is scalar. First order tensor is a vector. Second order tensor is a tensor. Second order tensor is basically we call it as a tensor. Why second order? Because it has a magnitude and it has a direction. Direction is in not only in one direction, but it has having components of other direction normal to the surface. So shear forces are basically not in the direction normal to the surface, but they have 2 component of forces, 2 direction of forces associated with that magnitude. That's why they are getting a tensor. So tensor, if we take an example in a solid object, if we give a stress here, the shear stress which is experienced is also tau x in the x direction, and some amount of shear stress due to the x will be in y direction, and some amount also will be in z direction if it's a solid cube. If it's an area, it's simply area, then some amount of tau shear stress will be in x direction. Some component of x shear, which here we have applied, will be in y direction. That will be denoted by tau xy. In the same manner, as given in the example, the shear stress is basically it has having a magnitude and direction, not in one also. There are 2 directions related to it. That is, it is acting on shear stress is acting on x, and also the some component of shear stress acting on y. So it's a tensor. Now our force vector is there and shear stress eta cap dA. Now we are interested in a normal component of the shear stress associated with our body forces, and we are integrating over that in the control surface here. Now we are having kept the LHS same. We are having del del T, volume integral of del del T of rho u dv plus area integral of rho u r and dm. Now please note that here we have replaced B, our any flow property, with velocity u. This is actually momentum. This is conservation of momentum equation. Momentum is what? Mass is velocity. That was basically we are solving Newton's second law of equation motion, and we now come to this equation. Rho p f b, divergence of tau. This is del dot tau is divergence of tau dv. Got this equation. Now if we solve that A, B, C, D, this is composed of four terms A, B, C, D. What are A, B, C, D? A is the body force acting on the fluid per unit volume. B is the stresses on the surface per unit volume. C is the rate of increase of momentum per unit volume. This is, and D is what? D is our momentum lost by advection per unit volume. So these are all D terms. Now please note that in D, that is divergence of rho uu, we are having as a form of a tensor. What is a divergence of rho u? Is a tensor. It's actually a dyadic product. What is dyadic product? Because the two vectors are making a tensor. There are two vectors, different vectors are present. They form a tensor. This velocity u is also a vector. This is u is also a vector. When we are giving this, the divergence of this, we are getting a dyadic product. This is known as a dyadic product. After simplifying and replacing the divergence of rho u from continuity equation, we get the form of equation something like this. Now if we continue solving this transport conservation momentum equation, we now get this equation as in written in equation number 1. Rho fb plus divergence of tau is rho du by dt. Now tau, what is tau here? Tau is the total stress. The total stress is basically composed of normal stress and deviatoric stress. Normal stress is the pressure stress due to the pressure, and deviatoric stress is acting some angle to the normal stress. Now this tau dash, this deviatoric stress, is composed of due to elasticity. If there is a two-phase flow, there is an elasticity between the phases, between the interface, or deformation tensor part. If it's a single phase flow, the film elasticity, that fluid film elasticity, or deformation, fluid deformation, and that stress associated is deformation tensor part. And vorticity, due to deformation, some vorticity or spin is getting aroused in that fluid, the spin tensor part. So it's given by, basically can be divided into J and K. J is half of grad of U plus grad of U transpose. Gradient of U is actually a vector. Grad of U is a vector, and we are getting a grad of U transpose. Now again, in the same manner, we are having vorticity part, which is the same but in antisymmetric way. Antisymmetric matrix, we are getting minus half of grad of U minus grad of U transpose. So if we replace all those systems in equation, we get tau dash, or our deviatoric stress part as 2 by 3 mu minus k divergence u, this mu grad u. For incompressible fluid, our divergence of u is 0. We all know by the definition of conservation of mass. And then our tau dash is gets the form of this equation. Now delta, our chronicle delta is 1 if the indices are same, and is 0 if indices are not same. If we replace all those terms in equation number 1, or we come back to Navier-Stokes equation, that is rho f b minus grad of p mu del square u rho du by dt. Here rho f b is our external forces, where minus grad of p is our pressure force, and we are having del square u as our convective velocity part, and we are having rho du by dt, which is a change of substantial time derivative of u with respect to t, which is a Lagrangian part. So divergence of u is incompressible flow. This is our well-known famous equation, that is Navier-Stokes equation. Similarly, we can also formulate energy balance equation with the help of Reynolds Transport Theorem, as is given discussed in this slide. We apply the divergence integral theorem, as we are familiar in this equation number 1. We write Reynolds Transport Theorem, then we convert area integral into volume integral with the help of divergence integral theorem. Then we del u, as we know, the q that is our total energy or work, and then the internal energy or energy is q minus delta w by the law of thermodynamics. We replace the same with the help, and this is our kinetic energy part, this is our potential energy part, this is our specific internal energy. So definitions are here given. That is heat. Q is your heat transfer into control volume. W is work done by the system. U is specific internal energy of the fluid. So we replace this. We come to this kind of equation. We can further solve. We get our this is our basic energy equation. In this way, we come to scaling analysis and dynamic similarity. What is scaling analysis and dynamic similarity? So this is used. We can get further insight into the equation by performing a scaling analysis. This allows the equation to become reduced to the least number of controlling parameters. Basically, scaling analysis is what? It reduces the number of factors required to analyze the equation, analyze the fluid flow in this context to least number of controlling parameters. So it scales down the equation, the problem to a least number of variables. The key variable U depends on several parameters as we earlier discussed, that is geometry, viscosity, density. If a systematic study is conducted and each parameter some range is done over some range are experimented, it will involve hundreds of experiments. So the technique for extracting the key controlling parameter or geometry is called non-dimensionalization. So this scaling analysis basically gives does non-dimensionalize and gives us our key controlling parameter. So that is why if there are 3 to 4 parameters here, we scale down the parameter scaling analysis and we come to the most important parameters, effective parameters, which is deciding reduced to least number of parameters, the main parameter which is deciding all the flow like problem or all the which is completely describing the problem, which is done. It is actually scaling analysis, and non-dimensionalization is an example of it. So by the non-dimensionalization, scale down and we get our Reynolds number as our scaling analysis. If we perform Navier-Stokes equations, there are other also Euler numbers also important, Ford numbers also important in context. We assign the values actually. If we take the example of a more popular Navier-Stokes equation, that is rho du by dt minus is equal to minus grad of p plus mu del square u plus rho g, we assign certain values, that is non-dimensionalized velocity, non-dimensionalized space, non-dimensionalized time, and non-dimensionalized delta vector, which is known as nabla. U star is equal to u by u. U is what? It's actually the ratio of two velocities. U is our characteristic velocity, which is fixed, which is the benchmark. And now we are having certain velocity u, and x star is x equal to x by l, which is our characteristic length l. What is characteristic length l? L is characteristic length is the diameter of a channel. Suppose there is a diameter of a channel, or there is a width of a channel. These are all characteristic length. Then we are having y star is equal to y by l, z star is equal to z by l. Non-dimensionalized time is there, which is the ratio of the time and the ratio of characteristic length to characteristic velocity. In this way it is found. So in non-dimensionalized calculation, we generally use Becquerel number as our non-dimensionalized time. The definition of non-dimensional time we will come later on. Then we are having delta star, which is denoted by L nabla. Nabla star is L nabla. So in this way, or we can say this is non-dimensionalized pressure P is minus P naught by rho u square. We are having non-dimensionalized frequency, which is F star is AF by F naught. So if we rearrange these values in equation, that equation earlier in the NS equation, Navier-Stokes equation, that in A, we find that if we rho du by u star, dl u by u t star, and all this we do substitution minus delta star by L, we put the value of pressure here and replace by substitution that this value. We take P star is equal to P minus P naught by rho u square. Replacing all these equations, we can come to a kind of a equation of sort du star by dt star minus del star P star by plus 1 by Re del square u star plus F naught F star L by rho u square. What are stars or this asterisk? Asterisk note this velocity, this term do not have any dimensions. That is, it is dimensionless. So by doing this dimensionless, we scale down all this number of parameters to a main critical parameters. What is that? That is Reynolds number. That is 1 by Re in this equation. So this is actually scaling analysis, and we do non-dimensionalize and found our key controlling parameters a Reynolds number. So in this way, we reduce the number of experiments to carry out all those uh, uh, to get the value or get the idea of a flow problem, flow field of interest. So where we have to do thousands or hundred of thousands of experiments, we just do a scaling analysis and bring down the number of experiments to here to hardly 10 to 15 or something like that. So we reduce the number of experiments to get the picture of how now our flow field of interest or problem of interest. So there's a video of a finite element simulation of two-phase flow. So I think